I'm Richard Corkish, I'm the manager of the Australian Centre for Advanced Photovoltaics, based here at UNSW. And after Mauro's talk, I'll give you a little introduction to that centre. Too quiet? I'll give you a little introduction to that centre, and then we're going to try and split you into 4 groups, and 2 groups will go up campus to the Solar Industrial Research Facility, and 2 will come here, and then we'll swap locations. So we've got some tour guides arranged for that. Welcome to your group. I hope you've been having a very useful and productive meeting here in Sydney, and thanks for coming to visit us here at UNSW. So I'd like to introduce the speaker, who's one of you. Most of you know him, I think. So Dr. Mauro Pravettoni. And Mauro is currently the Singapore convener of the IEC National Committee. He's a member of the British Society for the Philosophy of Science, and he's an assessor for our Australian NATA, National Association of Testing Authorities. His PhD is from Imperial College in London. Since 2017, he's been at the National University of Singapore, where he's the director of the PV module for urban solar cluster at SERIS. And from December 2023, next month, yes, he'll be appointed Senior Director at the Technology and Innovation Institute in Abu Dhabi. And, so thank you, Mauro, and welcome.
Thank you.
And he's going to tell us all about the reliability of modules in floating PV, stresses, severities, and tests. So we look forward to learning more about that. Thanks, Mauro.
Thank you, Richard, and thank you, colleagues and friends of UNSW for having given to me the opportunity to give this talk at SPRAE talk series. And of course, let me also thank for the organization of all the event of our IEC WG2 event, including this talk today. Chris Fell and his kind, request for me to have this talk. As Richard mentioned, the talk is about floating PV and is about specifically the reliability or the concerns on the reliability of modules that are being deployed in floating PV systems. Before moving to the technical topic, let me say a few words about my institute in Singapore. Is a National Research Institute, part of National University of Singapore. We have our grantors, which we'll always like to mention and thank. These are the National Resource Foundation, the Energy Market Authority, and the Economic Development Board in Singapore. Very broadly, we have 3 big clusters, right? One on cell, one on module, and one on system. You will see a little bit more on this in the next slides. More or less 120 staff plus PhD students, because we are an institute in a university, so it's very similar to the environment where we are now. But nevertheless, we are 9001 accredited as quality mark, but we are also 1705 accredited. Specifically, my laboratory, that I will show a little bit few slides there, is accredited for PV testing. As an institute that deals with applied science, solar energy, of course, we have strong and close collaborations with companies, so module manufacturers, but also from governmental agency, and of course with IEC. That's one of the reasons why I'm talking here today. So the main R&D areas of the institute are, as I mentioned, covering the areas of solar cells, solar modules, and solar systems. There's a picture there showing me while I'm measuring an incident angle modifier at module level. That's one topic that we discussed this week quite intensively. But yeah, the slide here lists a little bit of our topic. Let me see if I can go there with this. Yeah, there we are. I highlighted here in bold what are the topic that is being covered in this presentation, right? So module testing, module reliability, and floating, which somehow is the area covered is both the system and the module level. But here I'm focused on the module only. Floating PV is one of the 3 flagship projects of SERIS, together with perovskite, more specifically perovskite on silicon tandem structures, which is the flagship project of the cluster, of the cell cluster. With building integration PV, which is our own flagship project, although today I'm not talking about BIPV at all. And of course on the floating, which has been pioneered somehow together with other institutions worldwide, but with an important effort by my institute in the last years. Now here I want to show a little bit about my laboratory, for those of you who have never been there. We are located in an off-campus site from NUS in Singapore, and at level 6, this is what you find there, right? I try to use a color scheme. There is some climatic chamber that has various sizes. As you know now, the modules are gigantic, so we need to, have big chambers for them. Then we have, the blue boxes that are all related to irradiance tests, so solar simulators, both for high accuracy measurement, but also for light soaking, and UV testers. But probably what is more important to highlight here is the mechanical part, including the project for a floating PV testbed, for which I will say something at the end. Now, if you go out from the laboratory and you go down to level 1, now you enter and you will find very soon our recycling lab. So basically, this is a project for which we aim at achieving circularity. Module cell, in fact, come in the institutes, come in our laboratory. We can make module with a BIPV group. Then we test module with stress module. Eventually, we may destroy modules, and we want to recycle them. So here are some pictures taken by the machine we are going to install early next year, and level 1 in our institute. On the other side, if you go on the roof, then you enter in our outdoor test bed, which as all test bed have a light-induced degradation, research area, PID research area, which is very specific for our climate, and other reliability tests in progress. Plus, what we are planning and is mentioned there at the center as a SERIS testing, or what is it? Well, it may look like this one more or less. So the idea is to have at the same location a BIPV test bed with plug and play BIPV tests, and also a dome that opens when we want to measure in given conditions. That's it for introducing you to SERIS. And now from next slide onwards, I will enter in the topic of today, which is reliability for floating PV. So the starting point here is that what I call conventional PV, it's what I want to differentiate from what is going to be new in non-conventional PV. Now I'm talking to scholars, students, and experts, for which maybe this distinction is a little bit more gray now, because we all deal with new things, and new things are probably not really conventional. But for the sake of simplicity, I really divided here what I consider conventional, which means if you put a module on the roof or on in the field, well, that's well known, right? Is also new, always new, but at least it's conventional. I call it conventional. And what you put elsewhere, which I call it new integrated PV solution. In fact, my institute, together with other institutes, including Jülich, I believe, and other Chinese, representative, has launched 2 years ago a new workshop. New workshop are always welcome, right? A new workshop, an integrating PV workshop. So here we want to group really everything that goes on cars, on floating, on urban infrastructures, on building, because we believe that there is even more things new things to address, right? Including specifically what I'm saying today, reliability aspects. So here I group 3 of them, but there are several, of course, and the fantasy of our field and our manufacturers is never ending. So there will definitely be more in the future. Anyway, here we are talking about floating. Now, the market's perspective in fused lights is clearly growing. The interest is there, and every one of us can see. Is a little bit regional, still biased. It's not equal everywhere, right? But somehow all countries are looking with some interest in floating PV for various reasons. Here we see the gigawatt. So the floating solar installation in gigawatt DC foreseen up to 2026 to 4 gigawatt or so. This is an estimation provided by Wood Mac. Another agency shows here the floating solar market size. Again, linearly growing. We don't know, but in PV world, we often see something that starts linear and becomes exponential very soon. So it may continue linearly, it may stop, but there's also a chance that you can grow even further than these numbers. Now, I said is at the moment is still very, very geographically biased. It's mostly an Asian game at the moment, as you see in the color schemes here. We are where we are now. We are somewhere. Well, this is a little bit outdated, right? Where somehow here, I'm not sure if this estimation has been confirmed, but I think pretty much they are confirmed. So as you see, this is in percent, of course. So it's relatively speaking, China is dominating the installation and the market size, but with the important competition by India, South Korea. We all know this because this is, apart from me, that come from Singapore, although with the European background, these are the countries that are more active at the moment in our pre-normative activity. See the all others, which is always an area that is growing. So there are other countries. I think that worthy of mentioning the Netherlands for Europe, which is far the biggest one at the moment, and yeah, other countries most likely will follow. So here again is the countries that to cross 500 megawatt of cumulative floating PV power installations by 2031. Again, China, India, Indonesia, South Korea, Vietnam, Thailand, and downwards towards more other European countries. Worthy of mentioning USA, if not just for something that I told many people these days, episode, right? So I start presenting some ideas that came out to this presentation today, back in last February at the annual reliability workshop. And to my surprise, I think it was talking with George, but anyway, to my surprise, there was little on floating. And I was a little bit, coming from Singapore where floating isn't, everybody talks about floating, George press and whatever, then I was a little bit surprised. So I asked some colleagues from Enel why, and they say, Mauro, we have plenty of land, right? Why we should put solar on floater? Same argument may apply here. So most Australian friends here may have the same point of view, perspective. Why should we put on floating? We have plenty of availability of land. And then I was a little bit touched, saying, I'm stupid. Of course, that's true, right? I mean, Singapore has a problem. We'll see next slide with land, but definitely not all countries have this problem. So then on a following night where we were having a beer all together, then I was thinking about, but come on, China? China's not small, right? There's plenty of land there too, and why Chinese are putting so much on, pushing so much on floating? And then I asked a Chinese colleague, and he told me, you know what? There is this nexus between floating and fish farming, that the government is very interested, also to push a little bit the market, the economy of fishermen, right? If I say it like that. But anyway, there's this nexus which is of a lot of interest. So it means that it can be of interest also in other countries. They follow the same arguments or the same reasons. So talking about the scarcity of land and knowing that I was talking to Australian people, I mean, forgive me that I concentrate to New South Wales and not to full Australia. Otherwise, these numbers would have been, it's already ridiculous, but it would have been completely ridiculous, right? If I start talking about density of population in Australia. Then I say, okay, let us talk about not Sydney only, although it could be interesting to compare Sydney to Singapore, right? But let's talk about the country here, the state, so New South Wales. And these are the numbers, right? So 800,000 square kilometers, 8 million people. The density, of course, is very small. Now, where is Singapore? Well, Singapore is like that. It's always impressive, right? Singapore is a tiny island, right? It's, as you see, less than 1,000 times smaller than New South Wales. If you look at the chart here, those who are familiar with Australian geography, so the Australian us and others that already visited, if you see the capital's territory, well, it's pretty much the same. Smaller than the capital territory, but similar, right, as a size. So if you want to make a comparison, Singapore is probably 10 times smaller than the capital territory. And the population is I think the third or the fourth in the world in terms of density, and that's probably the driving reason, right? So we are highly densely populated, and we need energy, and we don't know where to put solar energy. I mean, we have somehow depleted all the possible options, and floating is the next one. But of course, floating comes with troubles, right? So the topic of my presentation is somehow shown here. Well, out of the impact of images, well, you don't necessarily have to put solar modules everywhere, right? I mean, you may avoid certain areas, but we know, and again, back to the idea of conventional versus non-conventional PV. I mean, you can't have a steady water, right? There will be waves. There will be some movement, which for us reliability experts in the room means there will be troubles there. Anyway, there is something we need to assess further. Not only, another problem is of course safety, and here there's a nice journal, press release by Emiliano, and it shows it's something happened this year, right? So basically, floating somehow landed in Hong Kong, and there are many problems, including that nobody knows where this comes from. So there's also some, someone should pay for the damage caused, right? That it's funny somehow for those who are not the owners of the plant, of course, but or the island, but we have to address something and to be sure that these problems not become more serious than they are. So I mentioned previously already that the story of SERIS with floating is not new. We started already some 5 plus years ago, right? Proposing, even more than that, let's say almost 10 years ago now, proposing floating PV as a solution for Singapore, and start liaising with stakeholders in the region and beyond the region, the Southeast Asia region. And biggest highlight of this research activity has been these 2 publications with the research with the World Bank, which you can download from our website. You just Google this, where sun meets the water, and you can download this for free. More or less heavily, what the findings that are described here later came in a national standard technical report, actually, that is supposed now to be promoted as an international technical report at the system level to describe lessons learned and best practices, these kind of things. Okay, here I just revised the most recent activity from 2021 to 2023, specifically with the research collaboration we are having with a Norwegian firm called Fredolsa Renewables, that are part of course, of the people that I need to acknowledge for this work. Starting in 2021 with technology mapping and financial modeling, ending this year, still ongoing in fact, with collaboration of DNV towards studying the problems at the module level. So again, the reliability, right, which is what I'm discussing today. As a result of this collaboration, we have identified slightly more than 100 possible new causes of failure, and we have compiled this risk matrix. So you see here from the horizontal scale, there is the probability class. So how likely can something happen in lifetime, right? We rate from 1 to 3, and is 1 when it's unlikely and 3 when it's very likely. And on the vertical scale, there's a severity class. And again, 1 when the severity we consider minor, and 3 when we think that the severity is high. So meaning that you need to replace the module or components. Of course, once you multiply the 2 in a matrix, then you have something that goes from 1 to 9. 1 you may suffer, you may accept it. 9 definitely you need to do something to prevent it, or take into account that this will happen more likely. Now I give you examples of failure that enter here. One example of what we consider, they will be raising hands here from my colleague from WG2, I believe. But anyway, whatever, I take the risk. What we consider mild in the particular environment of floating is the soiling due to snow formation of ice. Mild because maybe you don't want to put module at all in these very high, latitude regions. Or because anyway, this is something that may not be more problematic than what already happens on the roof. That's why it's considered in the green area of this risk matrix. Now, in the yellow area, there's event-based structural collapse. Here we are talking about a boat somehow that for whatever reason, because maybe the sea is problem, there's turbulence or whatever, crashes the plant. So that's something which is event-based and is risk that you need to do something, but it's probably unlikely, right? But anyway, you should take into consideration. A red case, and this is of course the subject of the last part of my presentation today, is the mechanical stress, particularly the module breakage that can occur due to certain mechanical stress. Here I highlighted the word torsion because we found, as you will see, that torsion stress is something particularly problematic. And something which is in the middle is PID in maritime environment. Now this has been pretty much debated. Should we do something more or less than what we already do? This is a big topic that I don't want to discuss here, but what is, I think, somehow agreed is that, of course, the presence of salt mist, the presence of salt, of ions, may increase the conductivity of the glass or the surface of the modules, and that can, of course, cause a more severe or a faster PID, which practically means that certain laboratories, even better, certain manufacturers that do PID tests and find that their module is mildly PID, so it's fine, then it should be more cautious when they put this module on the sea, because what seems to be mild in the normal standard test may be severe on the sea. So that's a little bit of the idea. Anyway, we judge this as kind of probable and partial damage, depending on how severe would be PID effect. So in order to better understand what I'm going to classify soon as a possible, new environmental condition and possible stresses and whatever, here we have classified floating system based of two bigger, somehow distinction, right? So one is anyway the module going to be in contact with water, yes or no? So, and on the left, you have the case where the module is physically separated from water. And on the right, you have the modules that are not physically separated from water. Now, in the two cases, then we divide again in two. The physical separation can be caused because the module is far from the water, still in a floating environment, but too far to be touched by water in any condition. Or because there's a medium that acts as a physical separation, so water cannot anyway touch the module. And when there is anyway the chance of contact with water, well, here we differentiate which kind of floating system we are talking about. If it's a rigid floating system, so that the module can move in this floating system, but somehow cannot move between each other, or when the buoy are non-rigidly joined, so that the module can move with more freedom. So this is an example in the sketch of physical separation. This is a membrane. This is a unique block of floater that moves all the system up and down, and this is a case where there is no rigidly buoyant. This is just my own drawing, so let's see a little bit of real pictures. Solar DAC proposes this big system, right, which is floating, and I guess none of you doubt that can rain, of course, but splash of a wave in this particular case is very unlikely, if possible at all, right? Now, insane energy, which is always my way I want to pronunciate this Norway serious manufacturer, which in fact is in sea energy, whatever. This is the example of a membrane, right? Where the separation is given by the material of the membrane. This is an example which I found on the rigid buoy, and this is an example which I found, by the way, at SNEC this year, and I believe those of you who are in the field have seen this several times, because this is probably the most diffuse floating system. And you can see why I think that here the more possible movement of modules, right? I mean, the difference between this system is a different in complexity, and it brings a different in risks somehow. We believe that low complexity goes towards high complexity from an engineering perspective in that direction, while the risk, of course, go in the opposite direction. The question of the developer or the owner, what they want to do, spend more and have less risk, or spend less and have more risk, these kind of things. So now we enter in the topic, having this in mind, so what we are talking about more or less, now we enter in the topic of module reliability, or closer to the topic of module reliability. Now the way we approached this has been, let us look at the standard, what is there. I mean, out a little bit of what we are used to do at the module level, and look what is out of the module level. So fortunately, there are two already series of standards, 6721, that lists the environmental conditions, and 6068 that lists the environmental testing. These two series of standards are correlated, right? So certain tests apply to certain environments. What we are used to is one of the things we are used to, but I mean probably the most obvious for my talk is the 61215 series of standard, which is module qualification. Very, in a very simplistic form, it means that a module that is commercialized and certified by certification bodies as a bare minimum has to pass this test, plus something else, right? But this test, it tells you the module, if I put in its environment, if you pass this test, we are quite sure that it will survive day one. It doesn't say it will survive 25 years, right? It says that it doesn't die the day after. Then there are other tests that can give you more confidence that the module will last for longer. Here I highlighted specifically certain tests that I think should be revisited. I'm not saying that the module that go to the sea do not have to pass these tests, but other than this, they should do something else, because the environment is different than the environment for which this scheme has been designed. And if you see, there are mostly mechanical tests that we think have argument to say that it's probably too mild for the situation, the environmental conditions in floating. Now, moving to the new environment, here basically in this set of tables, which I will not describe all in detail because it will take too long, but at least we show a little bit. So we are listing the environmental conditions as they are classified in the 6721 standard, and the description of what I'm talking about, the possible severities that you find in maritime environment, so taking the specifically that environment, and possible tests that we may want to introduce. Some of these are already there, some are not. Here I'm stopped for a few seconds on the first one, they call them heat environment. So that means anything that has depends on the climate and deals with the variation of temperature, right? And on heat. And a new stress test that I highlight here is the thermal shock. During our meetings this week, there's been some discussion about what does that mean, is that different from thermal cycling, which is a standard test we are already doing. Here I'm thinking about the thermal shock that your module, which is under the sun, in the middle of the sea or of the lake, in at noon, for which the module is probably at 60 degrees or so, and then there's some wave that comes through, splash your module, and the water is not at 60 degrees, right? The water is not even ambient temperature. It's clearly probably at 4. I mean, it depends on the season, right? And on the location, but it can be 4 degrees. In the most extreme severity that I found, the possible, variation air to water, as you see there, is 40 degree 5. This is considered an extreme variation. Air at 40 degrees and water at 5. But of course, the surface is hotter than 40 degrees, right? So the surface of the module may be 70, and here it's on us decide whether 70 is representative or you may have higher, because the module may have other reason to be hotter than this, but whatever. And 5, again, the temperature of water. So here the temperature of the module will move very rapidly from 70 degrees to 5. Are we stressing the modules this way? Well, the answer is clearly no. So we should consider whether it's possible to implement a new test to stress the module this way. Now, for the other stress test and climatic condition, we'll go a little bit faster in the interest of time, but trying to mention them. So the impact of water other than rain. modules are supposed to withstand rain, not only rain, hail, snow, this kind of environment, but on top of them, here we're talking about wave that can splash on the bottom or on the top of the module. And this is something that the normal module is not supposed to withstand. Here the severity is considered 10 meters per second in terms of speed of water. Now we enter in another classification, which is that of biological environment, right? So I mean, some stress that caused by for example, mold or fungus or rodents or these kind of things. We have already the ammonia test, which is not a qualification test. So module to be put on the market not necessarily have to pass the ammonia test, although it's already somehow a popular test to be done. It may become, let's say, a requirement if we go forward to qualification requirement for modules that go on the sea. And something else that, of course, at the material level, we are already trying to find. Here I put some symbol on what we think is critical. Again, moving forward to other climatic conditions, environmental conditions, not necessarily climatic. Here we have the chemical substances, similar to the biological, substances, but this is talking about chemical reactions, and so corrosion. And of course, the salt, if we're talking about floating in the maritime environment, so in the sea, that's definitely a concern. And as I mentioned previously, whether we want to consider a combination of PAD with a salt mist environment, it's something to be discussed. Other than the chemically active substances, there are mechanically active substances. So, sand or salt itself, it can act mechanically on the surface of the material. And also, I believe right on today, this morning, in our IC meeting, there was discussion about how the effect of abrasion can affect the quality of the module. So, may this also be considered at the material or the module level to be introduced. And finally, the mechanical stresses. So here I listed in total 3 different, lines. One is the stress due to stationary vibration. What I had in mind is the vibration, is the motion, right? Mostly the motion due to the sea, the waves, or the waves in lakes. Other kind of vibration, this can be caused by shock of water, and then the module start vibrating. And finally, the angular motion, we distinguish this to the vibration. We need to understand better what does the 6071 standard mean. Most likely it's really the movement, which in English is roll, pitch and yaw, right? All the movement of the boat, which now becomes a movement of the module that you need to take into consideration because it can cause torsion, which, as I already said, is critical. All of them, I think, are critical, as you will see in the last in this last part of my presentation that I'm entering now. So here I'm showing some results, examples from a set of tests that we have performed in the last 6 months or so at SERIS. And here I want to distinguish 2 big tests. One is PID with salt mist, and one that justifies what I said previously, that certain modules that suffer mild PID in standard condition see an accelerating effect if you put salt in if you do PID in salt mist conditions. I'm mentioning here some names where I know, but you will not see which module did what. This is for confidentiality, right? So we normally don't disclose that this module failed, this module passed. It's not fair. So, but just to show that we don't take unknown or modules that you have never heard. These are commercial modules. Just one clarification: the modules doing. I mean, you see the size, right? The module doing salt mist were small for one only reason, that at that time we did this test, our salt mist chamber was still an old one, could not fit the big module nowadays. Now we have a bigger one, and we can repeat these tests on large scale modules like the one you see that we have used to do mechanical stress test. I want to highlight one thing. You see for PID, one very old module, it was unknown at the time PID, so there's no indication in the old technical data sheet whether this module is PID free or not according to the manufacturer. Then we have one module by Trina that is clearly stated anti-PID, and another module which is considered PID resistant. Of course, this is a different wording. It may have different meaning. It may be just synonyms depending on how the commercial body of these manufacturers want to treat the PID free treatment or quality of their module. modules. For the mechanical part, similarly, so we have certain modules that are described as enhanced tolerance to mechanical loading. Some have no indication of mechanical strength. Some say is resistant to harsh environment, whichever it means, and durability and flexibility. But I want to stress this point. None of these modules are designed to floating officially, right? So these are the modules you can find on the market now. Possibly in the next years, I think I saw already something as SNEC this year. By the way, SNEC is the biggest exhibition of solar modules in Shanghai that occurs in May or early June, right, every year. And this year is SNEC. I remember I've seen clearly, I can't remember the manufacturer, by the way, but anyway, one big manufacturer was clearly saying this module is designed for floating PV. So I believe manufacturers are already distinguishing the production for floating or non-floating. And none of these have this classification. We need to be fair with these manufacturers because some of these you will see fail. I will not say which of those failed torsion, but whichever was them, they surely would say, Mauro, I didn't say that this module is resistant to torsion. Do you want a resistant to torsion module? I will make it one for you. Okay, anyway, start with PID in salt mist. This is the which now here I call PID prone, but it's not revealed. At that time, PID was unknown. It's a very old module. So, and incidentally, this module suffered PID. So on this particular module, who was known to suffer PID, you see the difference between the module that suffered PID in standard environments, a standard PID test. To be honest, this is not exactly a standard PID test. This is the old standard, 60 degrees Celsius instead of 85. And lost nearly 5% in standard conditions, with salt mist lost nearly double. The control module is the same module technology, did not enter in the chamber, right? And here you see what happens due to PID. This is a module that suffered PID, and this is a module that suffered more severe PID in salt mist conditions. Now, this is the PID-free module. It is indeed PID-free. We can only highlight that in one case, negative polarity, it was slightly less, slightly higher degradation. But to be honest, at this level, we can't really distinguish. It may be a reproducibility of the measurement. And here, a little bit more, we can say there's a little bit more evidence of PID, but again, not much difference between the PID in salt mist and PID in non-environment. Remember, this is considered PID resistance, this module. So, in fact, it is PID resistance. Those of us that are in the reliability and the standardization committee know that normally the 5% is the threshold, right? So if it fails, it means that it loses more than 5%. But clearly, if it loses 1%, you're not happy. But in principle, it's a pass. And here you see the two examples of the two cases who lost more, and the evidence of mild PID occurring in these grayer cells, right? Now, moving to the last of the set of measurements we have done, the one on mechanical stresses. Our benchmark was the dynamic mechanical load, because this is already a standard test. So the approach of the team was, okay, let us see if the module passes dynamic mechanical load, does it pass torsion or vibration? So basically, we are comparing these three tests. Standard dynamic mechanical load, here you see the specs for those of you who are not familiar with, so 1,000 cycles, 1,000 Pascal plus or minus, and the pressure is exerted at the center of the module, more or less for all manufacturers. So clamped in a way the manufacturer specifies at the corner typically, and pressed at the center, right? And typically to see if it pass or fails, you do pre and post Pmax and EL to see if there are cracks. The torsion we did, same, just changing the position of the pistons. You will see a movie shortly to see what I mean. So basically, we just took up all the pistons, clamped the module at the corners, and start pushing up and down at the other corners to generate torsion with the system we have without buying a new equipment. And I believe this is very easy for those who have a mechanical load test bed. Everybody can do, right? And then the question is how severe the stress. So we just use the same parameters of the dynamic mechanical load, just changing the torsion. Sorry for my animation. I'm sure that describes perfectly what I'm doing. You will see in a movie anyway. So here we are clamping half of the module and letting the other module vibrate with the vibration table, as you will see. Difficult to replicate the same as the the MLT. So here we decided to keep more or less a similar duration, so 8 hours. And the frequency, we look at the previous table where 3 Hz was somehow the frequency of motion of waves and whatever. So we kept 3 Hz. Yeah. So here you see the experiment in torsion mode. Tick 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 crick 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 maybe the frame, but usually is not. But anyway, that's what happened. And yeah, as I told you, basically this piston and the opposite piston, they are going up and down. The other pistons are all left, right, so released, and they don't make any pressure. And this is the vibration. So clamped at the center, we decided in this case to do this mixed vibration. So not only longitudinal or lateral, it's just mixed. Okay, on the vibration, actually I didn't specify previously on the table with the products. We took deliberately module with frame. But we also test this one at the beginning just to see where we are, right? Test to fail somehow. Let's see what happens. And stressed as much as we can to see when you see something. Because this is nothing, I mean, there will be no result to show, right? So at the beginning we took what we thought was the most fragile conditions, so frameless. And with frameless, no way. Not 8 hours, not even 1 hour. Okay, another one. Okay, no frame with frame, because with no frame there's little to see. So we tested all framed modules. And here we have the results. So this is the benchmark. Dynamic mechanical load. I actually forgot about how many modules were there. But anyway, we tested one module per type, per different manufacturer, and we had one control, right? So it could be 5 or 6. I made the box and whisker just to show something, right? And interestingly, the distribution you see here, which is centered to 0, well, that's just statistics, right? And this dashed line, which I draw here, is our intermediate precision conditions of measurements. Minor specification here, what does it mean? Okay, there are 3 different conditions of measurements when you want to compare different measurements, right? So you may want to do a measurement and repeat now. You don't touch anything. The instrument is still there. You just wait that the machine is ready to repeat the measurement. That is, strictly speaking, repeatability. And you have the minimum tolerance in variability. Anything that vary within repeatability, I mean, this is just nature. It's just the, science or whatever, the physics of the phenomenon you are studying is not repeatable. So if you repeat twice, for whatever reason, you have variation. But for example, variation in temperature doesn't cause this. Because unlikely, at the module level at least, on our world, unlikely if you repeat the measurement twice, you first do the measurement 25 degree and then you do the measurement 30 degree. I mean, likely the ambient temperature would be very similar, right? So you take out most of the potential sources of deviations in 2 measurements, and it's just the two possible repeatability, so the closest possible of results of 2 measurements. Now, it's completely different if I do the measurement and then I send to my colleagues in another institute in USA to repeat the measurement using the same procedure, but clearly different equipment because it's a different country and a different institute and different people. But that is called reproducibility. Of course, the measurement should be the same if we don't do errors, but the deviation, the tolerance of the deviation we may expect is bigger. This is intermediate precision, so something in between, because the measurement is not repeated now and now. It's now, then I wait 1 week when I do my test, and then I bring the module back, I try to position the same position, that's my accuracy, right? But still 1 week has passed, so it cannot be repeatability. We call it intermediate precision, better than reproducibility, because I'm still using the same system, same calibration, traceability, same whatever, even maybe same operator, right? So most of the things remain the same, but clearly there's a different amount of time that goes, for example, ambient changes, right, in the temperature and other things. And this is plus or minus 0.5% in power. This is our threshold. In summary, what does it mean? Means that any variation there, I can't judge, right? I can't say there's something happening. So it can be exactly the same thing. It may happen something, but I cannot say, right? What I can do, though, is taking the worst of the modules. If anything happens, well, that is the worst case, right? And you see the EL, there's nothing. So consistent with the fact that all these modules are commercially available, they are certified, and they passed the MLT, I confirm they passed the MLT. Okay, what happens if you do vibration? Still, there's a spread, Spread now goes a little bit towards the bottom part of my intermediate precision, but it's still within intermediate precision. So again, you can say too much, but there's a little bit of a change. So it's more those that lost something, that's something that, if it's a real intermediate precision, is up and down. If it's random, it's just something can gain, something can lose, but in fact, nothing happened. Here, there are more those that lost than those that gain, but again, not at a level in which I can say something. Although you see that the whisker falls down, the intermediate precision. So let's see that very module, and you see that very module has something here. I can't say that this is really causing that power loss. It could be, but anyway, something happened to this module, specifically where you may have expected something happen, right? Close to where the module is clamped. This is torsion. Torsion. Here we can say something happened. Most of the modules, more than half of the modules, suffer clearly some damage, right? Whether this is a pass or fail in our environment, we still have to decide, but clearly something happened, and obviously the DL confirmed that this is the worst case of the module. You see this line of stress where all the cells cracked and caused severe power degradation. Now, conclusions before few slides on the future work. Floating PV is gaining interest, no doubt. SERIS is pioneer research in floating PV at the system level for already 10 years. Now concerns of PV modules reliability. Since now it's coming to be a serious matter. It's not only a funny idea. Now concern reliability is becoming more important, so that in our environment, IEC, we are talking about that. We identified a risk matrix, and we found some critical, possible tests like PID or mechanical torsion. What are the further works? In my laboratory, we are now trying to explore vibration in cold environment down to 5 degrees Celsius, no more than that, because we can't put our vibration machine at minus something. But definitely this is something that can be done with other equipment. Explore propagation of cracks under vibration test. So maybe vibration test passes, but what happens if after a vibration test, then you do dump heat, and then you measure it again, or something else. Design accelerated stress test, which is more complicated, of course. Water impact, and analyze or propose mechanical or thermal stress for components. Here I propose a round robin on PID plus salt mist, but we will see about that thing. Most importantly, because this has been discussed this week, is to work at IEC to propose a new work item proposal, and to start having an international agreement on what to do on modules that go to the sea. Here is an example of the project that with one of my students thought, right, on how to splash water in a module in a laboratory environment, and this is what has been presented at IEC level this week. So we design a possible draft of new sequences for qualification of module for floating PV. All what is written in red is new, right? But this is clearly, inspired by 61215, so the chart that you saw at the beginning. There's an initial stabilization process, nothing really new. You want to be sure that when you start modules are stable. When you start the process of stress test, then you have all the part of stresses, and where again, as I said, the red tests here, which I label as FQT, different from NQT, which is the label of qualification of the qualification standard, where here is considered not alternative, but add on to this set of tests. The idea is again to see what is already done for the qualification and change what we think should be different, and try to see if it passes this test as well. And final, list of tests to be done to compare the initial and final measurements and see if the module has degraded or not. That is my presentation, and I want to really thank, apart from the guys that that help us to do this research, so Fred Olsen and DNV, but also my students and my staff at SERIS. As you heard from Richard at the beginning, I'm relocating soon to a new laboratory in a new environment. I've been very proud to work with them in these 6 years. So I'm extremely happy to present these results here in UNSW and UNSW, and thank them as well for the fantastic time I passed there in the last years. So thank you so much, and I'm very happy to answer questions.
Yeah, thank you very much, Mauro. And as you said, question time. Maybe you can field your own, perhaps.
Thank you. Kenji-san.
I can ask loudly. So I'm representing the WG9 working group for the structure. I'm a little bit concerned about the natural resonance of the array. So it may be nothing to do with the test for the module, but do you think that we have to consider about the resonance to the wave?
Do you mean on the whole structure or at the module level? Or the whole structure, right?
Whole structure, not the module level.
Okay, so it's a double question. So first of all, here I'm focusing by purpose only at the module level, right? Because I'm assuming that the other working group will work at the system level, at the structure level, and for which the answer is definitely yes, that should be done. At the module level, this is also a discussion which is somehow ongoing. So should we focus on the resonance frequency of the modules, which is known, depends on the size, or something else? Where here I clearly, deliberately somehow focus on the motion of water because it's not a free oscillation, what I have in mind, what I'm thinking about. So it's something that is driven up and down by the floaters, which may be different by, I don't know, but I'm guessing it may be different from the resonance frequency. But clearly, the resonance frequency is something that we also, what I'm expecting, the resonance frequency is just put something on the module and the module boom, 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 start fluctuating like free, right? Like a free body. But here is, I'm not sure how free is it because anyway it's clamped to a floaters, right? But anyway, definitely all this part needs to be investigated once we touch the vibration test.
Thank you.
Thank you.
Mauro, do you have, yeah.
Sorry.
Do I have to stand up too? Yeah. Do you have data like comparing like standard PID without salt and versus PID with salt? I'm just curious to see like if there's any significance, like does the salt aggravate like PID? Mm-hmm.
So in fact, the data I show goes somehow in that direction. The only problem is that we didn't do, again, for limitation of our equipment at that time, we didn't do the current standard, which is 85%. The main difference is temperature, right? It's higher temperature than it was before. It was at 60. So this test has been done at 60, which we know is a milder test. But the comparison there was from the same batch of production. Some module had done the standard PID and some have done the PID in salt mist. I want to clarify one thing because maybe I was a little bit quick. We didn't do sequential, we did combined. So it was literally PID performed in salt mist. So you put the module in salt mist, you start spraying salt, and then you soak it for some time, which is the 96 hours of the PID test, and then taking out, cleaning for salt and measuring. Just again, another additional information for those who are not familiar, salt mist test is a standalone test to check for corrosion, right? So normally a salt mist, you don't care if there is PID. You don't even look at it because you don't apply, by the way, any potential difference. So it's a different test. You want to be sure that the module, that the corrosion of the components, is not severe after a duration that depends on where you want to install and severities are classified. So that's basically the salt mist test. Here we are mixing a little bit up. That's why I call it a combined test. So basically we're doing the same thing on PID. The only thing is we add a spray for, if I remember correctly, 5 hours or so of spraying at the beginning, and then leave the module at the conditions of the normal PID, just that it was in a salt mist environment. So this is in fact what we have done. The only difference from your question is that we didn't use yet the current version of the standard, which is higher temperature, and we saw that the module that was labeled as unknown, which means too old to know somehow, and which somehow means also, yes, it suffered PID because at that time PID was not known, and most of the modules suffered, then it was known, then manufacturers made it differently. So that module was doubled. The power loss was doubled with respect to what happened in the standard PID. Christos.
So I just would like to place a remark. In TÜV Rheinland, we also test for floating PV, and we also have like a sequential where we perform salt mist corrosion test followed by PID. And the reason that we do the salt mist corrosion test is a preconditioning for the PID, because it will increase the surface conductivity and will possibly accelerate PID. So I think this is the reason that you want to do salt mist corrosion.
Yeah, I think I was just trying to clarify if you're doing it sequential, like you described, versus combined test.
Yeah, we have not really compared what happens if you compare a sequential case or a combined case and you get the same thing. Because if you get the same thing, maybe just easier to do, or at least allow laboratories to do sequentially, because maybe some laboratory can do combined. Yeah, Christos?
I just would like to say that basically we spray and we don't clean the PV module. So essentially it is combined. The salt stays on the top surface of the PV module. So if you clean it, it will be a different result. But if you don't clean the salt will remain there, so it should not have a difference.
Yeah, that's what exactly. I think that in the end the test will be very similar, apart from the normal reproducibility. Yeah. Reason why we don't at that time we were not doing that test is because we didn't want to put a salty module in our chamber that are not designed to withstand this, which I think is not the case for TÜV Rheinland. Yeah. So we bought a new salt mist chamber, then we can just plug the module in.
So for the projects I experienced in the past years, usually in China or in Japan, so the floating module was built in the lake, not on the seaside. So as you described, so maybe we have to divide into two scenarios or environments for the testing.
Yeah, at least. I totally agree. This was a question also coming out in our internal presentation at WG2, IEC WG2 this week. And it's totally, acceptable, and I totally agree on that. So clearly the environment, I mean, the environmental conditions listed in the standard which I cited only mention maritime environment as a chapter. But then in the maritime environment, there's a list of differences, right? Whether it is salty or reservoir, and of course the stresses are different. So I believe that your comment and your opinion that it should be different stresses depending on where you install is perfectly sound, and I believe perfectly agreed in this in the WG2 community.
Yeah, and another question. So based on your tests and your data, so in the future we will give some indication for the makers to do a module for the floating, because so now the module makers, so I don't think they have enough data to do such kind of design.
As far as I know, module manufacturers are already, well, not all probably, but some module manufacturers are already investigating and trial and error. Richard nicely introduced my beloved participation of the British Society for the Philosophy of Science, so trial and error. I mean, it reminds me some philosophers. But anyway, that's basically what the manufacturers are doing, and that precisely what at the moment is also the information which we are getting from them. But clearly, the final thing. First of all, I need to step back, and for those that look at this spray talk and those in the room that are not part of WG2, just want to clarify one thing. I mean, PV communities is PV industry and PV community is amazing because it's often the case that modules go on the market before there is a standard. Yeah. So God knows, what you can expect, because nobody knows how to measure, but they are already on the market. So the gentlemen in this room are really tough persons because they have to follow what is there. And I believe George, Tony, and Colleen and Peter can confirm that this WG2 and this technical committee is the most active in all IEC. And there are reasons, not because we are crazy and we don't know what to do on Saturday night, on that Friday afternoon. just because you guys, and again there are manufacturers here, are so fast and and invent things so fast that we have to somehow invent something to do for this. That's exactly one case, the floating. So you started your question saying, you're going to help the manufacturers to tell them what to do. Well, yes, in principle, yes, but practically mobile is the other way around. So it means that the manufacturer already put there and we need to check and then maybe suggest them what to do. But knowing the manufacturers that are not crazy persons, again, they are already doing something. And as I mentioned, right, when I stress modules, that doesn't say this is allowed to put on salt mist or on floating offshore. At the moment there isn't, at least the module I stressed, but I notice already something happening is next. So there are already some manufacturers that are already having in their portfolio modules that I think is robust enough to go at least in reservoirs.
Okay, thank you. Bye.
Okay, it's about the operation question.
Yeah.
I know you SERIS installed such a wonderful test bed in your seashore side, and I also had the experience in Korea, the test bed in Saemangeum area, and the big issue was soiling from the seagulls and seabirds dropping. How do you manage it in Singapore?
At the moment, we are observing. So that test bed you mentioned has been, I believe, or at least I heard, one of the first one to be designed specifically to get data, right, and to get information. And we are still learning from it. In my list, the biological, environment refers specifically to board drops and to whichever problem that can come from the fauna and flora, which is different than on a roof, right? So I think there's been some discussion this week about looking at the material level to see if there is anything that can be done to put resistant material to this. But at the moment, honestly, since your question was specific on SERIS, we are not really doing specific tests on this. We are mostly observing, trying to get data, and then in collaboration with IC, trying to design the most, relevant tests for that. Welcome.
Yeah. There was one.
Thank you for interesting talk. So I have one question regarding the salt mode testing. What kind of salt that you use for testing?
Oh, that was what chlorium. Sodium chloride. Yeah.
So as the float zone, float solar that put in the sea, it could be like the seawater would have different salt. Yeah. Besides like sodium chloride. Have you ever considering that?
I mean, there's, as I mentioned, there's a salt mist standard we are using, and we are just adapting to it. But there will be research on this, right? I can confirm what you say because we have installations on recently analyzed modules coming from after 10 years in the maritime environment Singapore, and yeah, you can find all different materials that come from the salt, right? Not only sodium chloride. Yeah. But yeah. Again, it's an open question, to be honest. And but the corrosion, one thing is the corrosion, so looking at the corrosion of it, and the other thing is looking at the deposition, the potential causes of hotspot caused by this deposition. PID has been discussed previously. So whatever can be, aggravated by the presence of salt, is under study.
Yep. The other question is like when you test the salt, do you like spray the salt on the front or on the rear side of that?
That's a good point. I believe on the front only. There's actually, at least in our chamber, but I think this is a standard specification, the modules are installed V-shape, and the spray comes from at the center. Then I think it disperses everywhere, to be honest, but it's sprayed on the top. So you find in the end most of the deposition on the top of the module, not on the rear. Some of these modules were bifacial, by the way, but that means anything because the property of the glass front and rear can be different. So it could be a good idea to spray on different sides and whatever.
The other thing, sorry, one more. So the last question is like you saw like a kind of mechanical stress test which is showing a bit of failure. So when you comparing like the glass and the glass backseat, which one do you see the most failure with the mechanical stress?
Wow, that's a good point. I go by memory because this test was done some time ago, and I believe that the largest failure was the glass backsheet module. But to be honest, we didn't see a specific trend. I think that there was something like that. So it really depends on the glass, on the material, on the size of the module.
There's no trend of glass or glass?
Not that I remember, to be perfectly honest with you, but I can check the data if you are interested, and I can get back to you, right? Yeah.
Thank you.
Thank you. I'd like to draw a hole. I know there's other questions, but Mauro will be with us this afternoon, I think.
Yeah, sure.
So maybe if you can catch up with him during the afternoon, that'd be good. Thank you. Because I think we need to try.
Thank you, Richard. Thank you.
Thank you.